Hello everyone, welcome back to your favorite and India's most affordable learning platform, Physics Wala. So in the last session of gravitation, in the lecture number 4, we discussed about the escape velocity and gravitational potential energy, right? So in continuation of this chapter, today we are going to deal with the lecture number 5, where we are going to focus on these topics. So one is orbital velocity, and then what is geostationary satellite and the energy of the satellite, and what is the binding energy of the satellite. So these are our main objectives for today's session. Okay guys, I just need your attention for the next 1 hour. Just be with me, avoid all the disturbances around you. And one more thing, at the end of the lecture, it's very important to prepare your own short notes. Okay now, and whatever the short notes that you prepared, revise them before coming to the next lecture. Okay, chalo. So let's get into the topic without wasting much time. So the first, let's start with a simple question. So what's the question says here? The earth is assumed to be a sphere of radius r. Fine. So a platform is arranged at a height r from the surface of the earth. Fine. So the escape velocity of a body from this platform is Fv, where v is the escape velocity from the surface of the earth. So the value of F is, see, simple question. So this is the surface of the earth. Consider, let's suppose, so this is the earth. So from the earth surface, so a platform is arranged at a height r from the surface of the earth. So here some platform is arranged, so which is at a height r from the surface of the earth. So this h is equals to r, this one, and we already have this distance as radius of the earth r s. Now, so if you throw an object, so the escape velocity of a body from this platform is Fv. So here the escape velocity from this platform, that means if you throw the body from here, it should escape the gravitational field of the earth. So let's suppose I am considering the escape velocity from here Ve dash. So and the escape velocity from the ground, let it be V, or else let's say V dash, let it be simply V dash, and let it be V. So we already know the gravitation, the escape velocity from the ground, what is of value? So root over 2gm by r. Yes. Now, so from this distance, from this height, what will be the escape velocity that they are asking? So if you are throwing with some velocity v dash, so now it reaches to some point infinity. Yes or no? It's escaping the gravitational field of the earth, means that distance we consider it as infinity, far distance. So the potential at infinity is 0 and the kinetic energy at infinity is considered 0. Now from here to here, let me apply the conservation of energy. So the conservation of mechanical energy. The conservation of mechanical energy I am applying from here to here. So let the initial potential energy, here it is Ui plus Ki is equals to Uf plus Kf. Done? Yes. So then what is the initial potential energy? So we have got, so this platform from here you are throwing the body of mass m. So the potential energy, the initial potential energy is G. Let the mass of the earth be m and the object has small m. So this object is at a distance is 2r from the surface of the from the earth center, because it is already at a height h is equals to r and the radius of the earth is r. So that I can write 2r, right? And then initial kinetic energy, you are throwing it with half m v dash square. So v dash square, right? So and then finally it's reaching some infinity point, it's escaping the gravitational field of the earth, right? So that's why final potential energy is 0, final kinetic energy is 0. That's it. So now you can simply substitute it here. So I can write, so minus gmm by 2r is equals to, so minus half m v dash square, let it be. So because those two are zeros, so minus gets cancelled, 2 gets cancelled, m gets cancelled. So we can write, so the v dash is equals to, the v dash square is equals to root over simply gm by r. So from here I get what is v dash, that v dash is equals to root over gm by r. Let it be the equation number 1. So now in the question they gave one hint. The escape velocity of a body from this platform is f into v. So this escape velocity is equals to f into v. So this escape velocity v dash, as per the given question, it is f into v, where v is the escape velocity from the surface of the earth. So v is the escape velocity from surface of earth. Escape velocity from surface of earth, whereas v dash is the escape velocity from h is equals to r, right? So from platform, so or else escape velocity from platform, better, right? So from platform. So this value they gave it in the question, so that v dash is equals to f into v. So we already calculated what is this v dash. What is that we got? Root over gm by r, yes, which is equals to frequency, f they gave some constant into. So what is the v? V is the escape velocity from the surface of the earth. So from the surface of the earth it's going to be root over 2gm by r, root over 2gm by r, yes. So from here root gm by r gets cancelled. So we left with here. So what's the remaining part? So 1 is equals to f into root 2. So I need what is the f value, right, as per the question. So what is the value of f? So I can write f is equals to, send this root 2 to this side, so which will be 1 by root 2 is the f value. Done? Clear, guys? Understood this concept? So let's check the option. So it's 1 by 2, no, root 2, no, 1 by root 2. Option C is the 3 is the correct one. Done? Very good. Chal. So let's move further. So now let's go for what is orbital velocity or the speed of the satellite. See, if any satellite is revolving around some planet whose mass is m. This is some planet whose mass is m, and let this planet has some radius r. So now a satellite is revolving or circling about this particular planet. So it can be Earth or some other planet. So around this planet is satellite is revolving, okay, with a velocity v0 in the circular path around the, not only can it cannot be circular path, so like it may be or may not be, okay. Chalo. So now I can write two things. So there will be some, the earth is of capital M mass and the satellite is of small m mass. So between those two there will be the gravitational force of attraction. So the Fg will be there, the gravitational force of attraction between those two bodies, because this is of some mass capital M and satellite is of mass small m, yes. And then so as it is revolving in the circular path, so there will be force which is centripetal, which acts towards the center of the earth, yes or no? So then I can say that, so these two forces will be equal. So the gravitational force will be equals to the centripetal force, yes. So let this orbital is revolving around the planet with a velocity v0, and then so here gravitational force formula, what's the gravitational force formula? So G m1 m2. So one is of mass m planet and the satellite is of small m mass by, so what is the distance between these two from here to the satellite? So the distance is r square, yes. So which is equals to, so what is the centripetal force? What is the centripetal force? So m v square by r m. So the velocity is v0 square. So the velocity is v0 square by the distance is r, I can write, yes or no? So now I need the orbital velocity. The orbital velocity is V naught I need. So here 1r gets cancelled and small m gets cancelled. So I can write V naught square is equals to Gm by R. Right? So from here, so the V naught is equals to root over Gm by R. So this is the orbital velocity formula. So this is a formula for the orbital velocity. This is the formula for the orbital velocity, guys. Then, so if you want, you can write this formula in terms of small g and r also. So how do we write? We know that g is equals to Gm by r square. G is equals to Gm by r square. So from here, so the capital Gm is equals to small g r square. Shall we write? Yes or no? So now I can write here. So the V orbital is equals to root over G r square by r. So root over G r, yes or no? So this is Gm by r square, which is nothing but G r square by r. So then you can also write it as V naught is equals to, so root r square, if you can bring it out, so root over G by r. So where this r is a distance, see, this capital R is a radius of the earth or planet, whatever the planet around which the satellite is revolving. And then this r is at what distance from the planet center it is revolving. So this distance, small r is this distance, whereas capital R is a radius of the planet. So generally we take earth here, so around the earth. So that's why, so we keep here 6.4 into 10 to the power 6 mostly if they mention it in the question. So is this part clear, guys? The orbital velocity concept clear? What's the formula in terms of Gm by r? And then so here in terms of small g also we wrote the formula. So just have a look at that one. Clear? Any doubt here? Any doubt related to this? Fine. Chal. Next. So let's go for the next question or concept. Let's see. So try this question on your own. I just stand aside. So a satellite circled around the earth, so at a distance 3400 kilometers. So determine its orbital velocity if the radius of the earth is 6400 kilometers. So and g value, small g value is 9.8 meter per second square. So the simple question, see here, first consider this is the earth and then a satellite is revolving around the earth. A satellite is revolving around the earth at a distance 3400 kilometers. So this is the radius of the earth, and from here to here again it is 3400 kilometers. Okay, so what will be the total? This distance is called the small r distance. So what is the small r distance here? Small r is equals to, so the radius of the earth plus 3400 kilometers. Okay, so what is this radius of the earth? So 6400 kilometers plus 3400 kilometers, right? So this we get it as, so we can write 64 plus 34, so which is 9800. Yes or no? Yes, fine. So this is kilometers, so we can write into 10 to the power 3 r. So let's write 9.8 into 10 to the power 6 meter. Okay, fine. This is r value. So now they gave the small g value, you know the r value. So they are asking orbital velocity. Let me use this formula for the orbital velocity. VO is equals to r into square root of g by small r. I'll use this formula because I know the small g value. They mentioned it in the question, and r value I got it, and capital R value I know it. So then simply substitute. So we need it in meter per second. All the options are in meter per second. So write this r in terms of meter per second only. So meters only. So r is 6.4 into 10 to the power 6. So root. So this is 9.8 by. So here 9.8 into 10 to the power 6, right? So 9.8 gets cancelled. So we can write, so 6.4 into 10 to the power 6 into, so what is this square root of 1 by 10 to the power 6 means 1 by 10 cube whole square. So we can write it as square root gets cancelled. I can write 1 by 10 to the power 3 here. Simple calculations, always do the simple calculations. So send it to upside, 6.4 into 10 to the power 3. So which is nothing but 6400 meter per second. So 6400 meter per second. Option 3 is the correct one. Understood guys? Clear? Any doubt here? Simple concept. Just a formula based question. Sure. So let's move further. Chalo. So we have one more question here. So the question number 3. A remote sensing satellite of Earth revolves in a circular orbit at a height. This is the height above the surface of the Earth. So if the Earth's radius is 6.38 into 10 to the power 6. If they mention it in the question, take that value only. Okay. So actually we generally take 6.4 into 10 to the power 6, right? So here in the question they mentioned 6.38 into 10 to the power 6. So take that value only. Okay. And then G value also they mentioned. So then the orbital speed. Again the formula based question. Simple question. First understand here. So this is the Earth. So from Earth's surface, so the satellite is revolving at a height of 0.25 into 10 to the power 6. So that means here, let's suppose the satellite is revolving like this around the Earth. So this is the Earth radius r. We know this. This is the Earth radius r. And what will be this distance they gave from here to here? From here to here. So the distance that they gave it as, this is the height h. Right. So this is the whole thing is a small r. So let's write this way. So now I need the small r distance, which is r plus h. The small r is from the center of the Earth to the satellite. So whatever the distance is, the small r, which is radius of the Earth plus the height from the Earth where the satellite is revolving. So then radius of the Earth, they gave it in the question 6.38 into 10 to the power 6. And the height, at what height it is revolving? 0.25 into 10 to the power 6. So if you take 10 to the power 6 common, so 6.38 plus 0.25, which is 6.63. Yes or no? So into 10 to the power 6 meters. So we got the small r value, we got the G value. So and then simply substitute. So G value is equals to 9.8 meter per second square. So now let me write the orbital velocity formula in terms of, so capital R and small g and small r. So what is that formula? VO is equals to r into root over g by r. So now do the simple calculations. So what is r, which is 6.38 into 10 to the power 6 into root over g value 9.8 by, so what is the small r value? So 6.63 into 10 to the power 6. So you can bring this 10 to the power 6 outside. So 6.38 into 10 to the power 6 by 10 to the power 3, I am bringing it out. So and root of, so 9.8 by 6.6, let's write. So this will be, so in which table it goes? So in which table it goes? So 12. So 3 table, let's write. So 3 threes are, no. So it goes in 2 table, 4.9 by 3.3. So which is nothing but 49 by 3. So which is, we can write it as 11 fours are 11 5 3 5 by 3. 5 by 3 means 1 point something. So choose the closest option. So 10 to the power 3 means 6.38. This will come out to be somewhere 1 point something, root over 1 point something into 10 to the power 3. So this is 1 point something, you will get 1.1 or 1.2. So closely, I'll choose the approximate value because the values are bit far only. So 6.38 into 1.1 or 1.2, something like 6.67 I can get. So this is the closest value. Yes or no? So I'll go for this one, 6.67 kilometer per second. Done? Understood guys? Everyone? Just take care of the calculations, that's it. Okay, so one more value is also closer, so better let's solve because so this is already 6.38 into 10 to the power 3 into, so this is 4.49 by 33. So or else let's write something like root of 1.12. So 12 means 1.11, 1.2 something like that. So see, it comes out to be somewhere around 7 point something. So you can choose this option, guys. Okay, so if you want you can do the calculation. So go for the second option because it cannot be, because 6.38 and very close one, no. So 7.76 I'll do. Okay, now done. Chal. Next. So let's go for the next one. So try this question on your own. The radii of circular orbits of two satellites A and B of the Earth are 4r and r respectively. So if the satellite A is 3v, so if the speed of satellite A is 3v, so then the speed of satellite B will be, okay. So this is the Earth. From Earth there are two satellites. So this is consider satellite A and this is satellite B. So this is A, let's say this is B. So the A satellite is revolving with a speed 3v. So now what is the velocity of the satellite B? So let it be v dash. Okay, so they are 4r and r respectively. A is 4r, so let's take A outside, B inside. So A is 4r and then B is r. So this distance. So from where it is? So from the surface of the Earth. These distances are always from the surface of the Earth, guys. Don't take from the center. So for this first one, what will be this total distance? 5r. So for the second one, this is total. This total distance will be r plus r. This will be 2r and this distance will be total 5r it will be. Okay. Now you can do the calculations easily. Yes or no? Chal. Do the calculations. See, simple thing, right? So let's write, let it be the velocity of B. So this is we considered as A, this is we considered as B, right? So the velocity of satellite B, what is the formula? So root over G mass of the satellite, let it be M. So the radii of circular orbits of by G earth mass is M by, so what is the R? What's the R formula we can write? R of the satellite B, let's write. So then for the A it is going to be root over GM by, so R of A. So let's do one thing. So let's do VB by VA. Simple calculations. Root over GM by RB by root over GM by RA, right? So I can write, so root GM gets cancelled. So VB by VA is equals to, so root over RA by RB will come, right? So from here, so what is the root over here I can, yes or no? So root over RA by RB. So what is root over RA? RA is radius of the first one is 4r and the radius of the RB is r. So this is 2. Root 4 is 2. So VB by VA is 2. So then VB we required, which is 2 into VA. So the velocity of the orbit A is given, which is 2 into 3V, guys. So which is nothing but 6V is the correct answer. So option 2. Okay now. So done. Clear? Understood everyone? Sure. See, always do the complete calculations, or you left the calculations here. If you want, I can do it, no issue. So see here. You can take the values. So here I can directly write this as, let's do one thing. This is, so 9.8 by 6.6 I am writing. So which is root over 98 by 66. So let's write 6.38 into, so 10 to the power 3. So here I am writing, so I am taking this close to 100, this one close to 64. Okay. So then I can write 10 by 8. I can write 10 by 8. So 2 4s are 2 5s are, right? So 5 by 4 means 1.25. 6.38 into 10 to the power 3 into now 1.25. 1.25. Yes or no? So then you can multiply 6.38 and 1.25. So however, you'll get somewhere around 7.76. Previously I told you to multiply it with 1.2. So then also you'll get the same thing. Okay. So this also done. 6V is the correct answer. Chalo. So you guys should practice the calculations. Okay. Done. Yes. So now if the satellite is revolving very close to the earth, see here, this is the earth. So previously we considered the radius of the earth is r, and from the surface of the earth, so it is at some height h, so that we consider this distance as r. Okay. So now if the satellite is revolving very close to earth, if satellite is revolving very close to earth, so in such cases, so we can consider, so the small r distance is approximately equals to the radius of the earth, because it is revolving very near to the earth's surface. So the radius of the earth will become the distance between the center of the earth to the satellite. Okay, so the small r will be approximately equals to, so r. So and orbital speed, what's the orbital speed will become? We know the formula for the orbital speed is VO is equals to root over gm by r. So that's what we got in the starting. So VO is equals to root over gm by r. So now in place of this small r, I'll substitute. So this VO is equals to root over gm by capital R. Root over gm by capital R. Or else, so you can write in this way also. Which one? So we have got, so the orbital velocity is equals to root over gm by r. So we know that g is equals to gm by r square from here. So gm is equals to gr square. Gm is equals to gr square. So now the orbital speed VO will be equals to root over, so what is gm? So I can write gr square by r. So r gets cancelled. So v orbital speed is root gr. V orbital speed is root gr. So you know the value of small g and you know the value of capital R. So the small g value we take 9.8 meter per second square, right? And r value in terms of meters, so 6.4 into 10 to the power 6 meters. Yes, understanding guys? So just simple concept, that's it. We are just modifying from one formula to another formula, that's it. Okay, so if you substitute those values, what should be the answer? The orbital speed of a satellite which is very close to the earth, so you can simply write VO is equals to root gr. So this value approximately comes out to be 8 kilometer per second. How much? 8 kilometer per second. Okay, done guys. Chalo. So simply remember now the orbital speed VO is equals to root over gm by r, and VO is equals to root gr. So when these two formulas are applicable, when the satellite is revolving near the earth surface, the small r will be approximately equals to the capital R. Done? Any confusion here? No. Chalo. So let's move further. Chalo. So we have got one question here. So try to solve this question guys. Try to solve this question on your own. A satellite is launched into a circular orbit close to the earth's surface. So close to the earth's surface. So what additional velocity has new to be imparted to the satellite in the orbit to overcome the gravitational pull? See here. So a satellite is launched into a circular orbit very close to the earth's surface. See here. So underline this statement. So into a circular orbit close to the earth's surface. It is close to the earth's surface. Done? Sure. So with what additional velocity has new to be imparted to the satellite in the orbit so that it overcomes the gravitational pull? Because it has to revolve in the circular path, right? If it is pulled by the earth, so it will fall into the Earth. Yes or no? Understanding? It has to overcome the gravitational pull. Then only it can revolve around the Earth. Chalo. So try this question on your own. This is a Earth. Just try this question on your own. So it is revolving very near to the Earth surface. Chalo. So what if it is near to the Earth surface? What is the orbital speed we have? What is the orbital speed if it is very near to the Earth surface? So the v orbital when it is very close to the Earth surface is root over gm by r, which we can also write it as, so gr square by r. So r gets cancelled, root gr. So this is what we got. Now, so what should be the new velocity? What should be the new velocity? Let it be some v dash. So how do you write the v dash velocity formula now? Write the v dash velocity. The escape velocity formula you can write simply. Yes or no? It has to overcome the gravitational pull. So that means it has to gain escape velocity, right? So what is that velocity? So v o dash, or else the v dash is equals to root over 2gm by r. Root over 2gm by r. That's it. So now you substitute the value. So what is the r? Very close to the Earth surface means this r value you can take it as root gm by r. Yes. So then this is root gm by r. This is root 2gm by r. So the new additional velocity. The new additional velocity. Simply subtract these two. So v dash minus vo. So do the calculations. What we are going to get this value? Simply subtract. See, either you can write in terms of this gr, or else you can write this way. So here in place of this root, in place of gm, I am writing gr square by r gets cancelled, root 2gr. So this will be easier one, I guess. So v dash minus v means, let's write in terms of small g's only, both root 2gr minus root gr. So here let me take root gr common, so that it will be root 2 minus 1. So what's the value of root gr, which is already we got somewhere around 8 km per second. Previously I told you, right? So this root gr value is somewhere around 8 km per second into this root 2 minus 1, which is 1.414 minus 1. So 8 into 0.414. So 8 into 0.414. So 8 into 0.5. So approximately 0.5, which will be somewhere around 4 point something. So what's the option which is closer to the 4? What is the answer which is closer to the 4 there? See here, I have got only the 3.278, right? Understanding? This is the one which, because we are not taking 0.5 directly, it is less than the 0.5, so that it will come below 4. So which is 3.278. Done? Everyone? Clear, guys? Chal. Next, so let's move further. So what is the relation between the orbital speed and the escape speed? So we have got the orbital speed formula. So root over gm by r. Yes. So then, so what is the escape speed formula? So root over 2gm by r. Yes or no? So now, so let me do one thing. So let it be equation number 1. Let it be equation number 2. So then the VE by VO. Let's divide those two equations. So 2 by 1. So just to get the relation between those two. The escape velocity we are finding from some distance, not only the Earth. So if it is for the Earth, we can write the capital R. So I am writing it for some general planet. So for the general planet, let it be the R. Okay. So then the orbital speed for some general planet, let it be the small r. Okay. So here we can write root over 2gm by r by, so root over gm by r. So I can cancel root gm by r, root gm by r. So that I got, so VE by VO is equals to root 2. So we can write here the escape velocity is equals to root 2 times the orbital velocity. The escape velocity is root 2 times the orbital velocity. So direct formula, so which can, the question can be framed directly based on this. Okay now, so the question can be asked very directly based on these concepts. So remember this statement directly. Done guys. Chalo. So let's move further. So VE is the escape velocity and V0 is the orbital velocity of a satellite. See here, not for the Earth we are writing. Sir, why you are taking small r here? So it might be the doubt for students. So if I take Earth, so then I'll write capital R, but I am taking it for some general planet. That's why I'm going for small r. Okay, chalo. So what's for satellite orbit close to the Earth's surface? So then these are related by. So if they are close to the Earth's surface, so we can write Gm by capital R. Here 2Gm by capital R. That's it. So however, again Gm by R gets cancelled. Root over Gm by R gets cancelled. We left with root 2 only. Okay, so if you want, if they are very close to the Earth's surface, just write it as root over Gm by capital R. So here also root over 2 Gm by capital R. So then also root over Gm by R, root over Gm by R gets cancels. Again we get the same thing. So here also the same. Okay, so what is the relation between the escape velocity and the orbital velocity? The escape velocity will be root 2 times the orbital velocity. Not root for the both. Only for root 2, and V0 should be outside. The orbital velocity should be outside the root. Done? Chalo. Clear. So now, what is the time period of revolution of the satellite? See, if an orbital, if a satellite of mass m is revolving around some planet, so which is of radius r, or else which is of some distance, which is at a distance small r distance from the planet, of the center of the planet. So it is moving with a velocity V0. So for one complete revolution, this satellite covers how much distance? Tell me. For one complete revolution, so this satellite covers, so the distance of 2 pi r. The 2 pi r. So what is the time period formula? So the distance covered in one complete revolution, and by with what speed it is covering the distance. Yes or no? So the distance covered in one revolution, the distance covered in one revolution by the time t, the speed with which it is revolving around the planet. So the time period t is equals to, so here for one complete revolution it's covering a distance of 2 pi r. Yes. Then so with what speed it is revolving around the satellite? So orbital around the planet. So with orbital speed VO. So now you can write the formula easily. So which we can write it as, so 2 pi r. So here root over Gm by r, the orbital speed, already we know this one. So from here, so let me write, so let's write it in the next slide. So t is equals to, I have got, so 2 pi r by root over Gm by r. So here t is equals to 2 pi r into root over r by Gm. So let's do one thing. So let's write this r also inside. If we send r to the root, inside the root, so it will become r square. So 2 pi into root over r cube by Gm. So this is the time period of the satellite. So this is the time period of satellite. Time period of the satellite. Clear guys? Done? So if it is very close to the Earth's surface, we take this r as capital R cube. That's it. Okay. Then, so here one important result that you have to understand is, so the 2 pi is a constant, and so g is a constant, and m is a mass of the planet. If we take Earth, we take the mass of the Earth, or some other planet, we take the mass of that planet. So this is also constant. So the r changes, the distance around the planet at which it revolves, this varies. So I can write like, so the t is directly proportional to root r cube. The t is directly proportional to root r cube. So here I can do square on either side. So t square is directly proportional to r cube. The very, very important result. So the t square is directly proportional to r cube. So where we can write, so t dash by t whole square is equals to r dash by r whole cube. We can write this. So this is a very, very important result. You should remember, guys, from the time period of the satellite. Okay, so this is also called the Kepler law actually. Which Kepler law? So it's a Kepler's third law. It's a Kepler's third law. It's a Kepler's third law. This one. Done, guys? Chalo. So we have studied the Kepler's third law also. Just have a look at these formulas, because many formulas will come in this chapter. Okay, so you have to write all these formulas at one place. Then only you can remember them. Done? Chalo. Chalo. So done. See here, and one more thing. Let me tell you one more theory question also. So we have got orbital speed is equals to root over gm by r, and we have got time period is equals to 2 pi into root over r cube by gm. So if you observe the orbital speed and the time period of the satellite, they both are independent of the mass of the satellite. So I'll write that statement here. So the v naught orbital speed and the time period, they both are independent of mass of the satellite. They both are independent of mass of the satellite. Why? Are you guys seeing any small m mass here? The satellite is of mass how much? Small m. So in this orbital speed or time period formula, there is no small m term, right? So I can say that the orbital speed and time period are independent of the mass of the satellite. Done, guys? Clear? Chal. Good. Next. So let's move further. So try this question. Let's try this question on your own, everyone. So what's the question says? A satellite A of mass m is at a distance r from the center of the earth. So and then a satellite B is of mass 2m is at a distance 2r from the center of the earth. So the time periods are in the ratio. See, the first thing is time period is independent of the mass, but the time period, it depends on the distance of the satellite from the center of the planet. So here the planet they mentioned Earth, right? So from the center of the Earth, one planet is at a distance r and the another planet is at a distance 2r. So consider, let's suppose this is a Earth. So around the here, so one planet is at a distance r and the another planet which is at a distance 2r. So another planet is at a distance 2r. Now, so we know that the time period is directly proportional to t square is directly proportional to r cube. I'll use this relation because I just need the time period depends on the distance of the satellite from the center of the planet, right? So here I'll write, so let the ta square by or else ta by tb whole square is equals to RA by RB whole cube. RA by RB whole cube. So then simply write, so TA, let it be. So and then by TB whole square, the time periods ratio we required. Okay, fine. So this one, So then I can write this as, what is RA? The first one is of the radius, A is of mass m and radius r. And the second one is of the radius 2r whole cube. Done. So here r gets cancelled. So the TA by TB whole square is equals to, so 1 by 2 whole cube, which is nothing but 1 by 8. So where I can write TA by TB is equals to, send this square to that side, so which will be, so root over 1 by 8. So TA by TB is equals to, so 1 by, so root 8. So root 8 I can write as 4 into 2. So 4, if it comes out, 2 root 2. So that means 1 is to 2 root 2 is the correct answer. 1 is to 2 root 2. So the TA is to TB is 1 is to 2 root 2. Done? Option 4 is the correct one, guys. Clear, everyone? Chalo, good. Now the time period of the satellite very close to the earth surface. See here, the same concept. Let's say this is a earth. So now the satellite is very close to the earth surface now. So this is a satellite of small m mass, and this is the earth of mass m and radius r. So now here this distance is small r. So if it is very close to earth surface, we can consider the small r is approximately equals to capital R. We have got the time period formula as 2 pi into root over r cube by gm. Root over r cube by gm. So I can write, in place of this small r, so I can write capital R cube by gm. That's it. So this is one way. Or else you can also write it in terms of the small g. How do you write it in terms of the small g? So t is equals to 2 pi into root over r cube by, so in place of gm, so I'll write g r square. In place of gm, I'll write g r square. So r square r cube gets cancelled. So t is equals to 2 pi into root over r by, so we have got g, root over r by g. So all these values are constants here. The 2 is a constant, pi is a constant, capital R is a constant, and g is a constant. Here also 2 is a constant, pi is a constant, r is a constant, g is a constant, and m is a constant. So every value is constant. You can simply substitute their values there. You can simply substitute their values. So then the time period it comes out to be, if it is very close to the earth, so substituting the values, it comes out to be somewhere around 84 minutes, guys, which is 1.4 hours. Done? Chalo. So remember this. Done, everyone. Hope the concepts are getting cleared. So these formulas you can't remember just at a time once, but you should practice them. Okay. So then, what is the geostationary satellite? A satellite whose time period is 24 hours and it moves in the same sense of rotation as of the earth. So if the earth is rotating this way, so the satellite also should rotate around the earth in the same sense of rotation. So then, and the time period of that satellite should be 24 hours. What is the time period? So to complete one revolution around the earth, it should take 24 hours. So then, so that satellite is called the geostationary satellite. So what are the conditions, or two conditions for the geostationary satellite? So its time period should be 24 hours, right? That means to complete one revolution, it should take 24 hours. And then the second condition, so it should rotate around the earth in the same direction as of the earth rotates. So see here, so let's suppose this is the earth. If it is rotating about this axis, so the satellite of mass m is there near the earth surface. So then this also should rotate in the same rotation as of the earth. Okay, so the omega of earth should be equals to, so the omega of the satellite. The omega of the earth should be equals to the omega of the satellite. Same. And then, so the omega should be in the same direction. Done? And then, So as seen from the earth, the satellite will appear to be stationary because it is rotating same. See, let's suppose you are sitting inside the bus, okay, and your friend is also beside you. Then if you observe your friend in a moving bus, you both will be seen in rest with respect to one another. Same way here also. So the earth is rotating and a satellite is also rotating with the same omega and same direction. So then we can say that if the earth observes the satellite, so the satellite seems to be at rest. If the satellite observes the earth, so the earth seems to be at rest with respect to the satellite. Yes, that's what the statement here. As seen from the earth, so the satellite will appear to be stationary in this case. Clear? So two conditions for the geostationary satellite. Time period should be 24 hours and the rotation should be of the same sense as of the earth. Done? Chalo. So let's write that part. So what is the time period formula? You know the time period formula, right? So the time period should be 2 pi by omega. They both will have the same time period, 2 pi by omega. Chalo, done. Next. So let's try this question on your own, guys. Try this question on your own. The mean radius of the earth is r and its angular speed on its own axis is omega, and the acceleration due to earth's surface is g. What will be the radius of the orbit of geostationary satellite? So you have to find what is the radius of the geostationary satellite. So try this question on your own. See, we know that the time period of the geostationary satellite and time period of the earth's rotation should be same. Yes? Yes or no? See, simple concept. So the time period of the earth, so the time period of the geostationary satellite should be same. So the time period of the earth, we know that t is equals to 2 pi by omega, right? So which is equals to, what is the satellite time period? What is the satellite time period formula that just now we have got? So 2 pi into, so root over r cube by gm. That's it. So now you do the calculations and find the omega value. So simply do the calculations and find the omega value. Do the simple calculations and find the omega value. That's it. What is there? Just do the simple calculations. No, 2 pi cancel. 1 by omega is equals to root over r cube by gm. So then we have got, so 1 by omega. So let's do square on either side. So that 1 by omega square. 1 square is 1. So omega square is equals to r cube by gm. R cube by gm. So from here I need omega actually. Sorry guys. So I need omega here. So the omega square is equals to gm by r cube. Omega square is equals to gm by r cube. So from here omega is equals to root over gm by r cube. So root over gm by r cube. So I need it in terms of which one? I need it in terms of, so capital R. So in place of small r, you can substitute the capital R. So I need, what is the radius I required? Sorry, not omega. I need radius. So my bad. See here. So r cube is equals to gm by omega square. Yes, from here. So the r cube is equals to, so in place of this gm, I am writing gr square, because I need in small g and capital R. So by omega square. Done? Yes. So now r is equals to, so gr square by omega square whole to the power, so 1 by 3. If this cube send it to that side, so it will be 1 by 3. So gr square or r square g by omega square whole to the power 1 by 3. Option 1 is the correct one. They asked for the radius. Done? Clear everyone? So this concept is done. Chalo. So let's move further. Chalo. So let's go for the next question. A geostationary satellite is orbiting the earth at a height phi r above the surface of the earth. So and r being the radius of the earth, so the time period of the satellite, another satellite in our at a height 2r from the surface of the earth. So there are two satellites. So the first satellite is at a height of 5r from the surface of the earth. So this height is 5r from the surface of the earth. So what will be the small r now? So the small r will become 6r, because the radius of the earth also you should include that. And then so another satellite which is at a distance 2r from the surface of the earth. So this distance is 2r from the surface of the earth. So now let it be the satellite A, let it be the satellite B. So they are asking what is the time period of the another satellite. So the TA is a geostationary satellite, the first one, 24 hours we can substitute, and then TB we have to find. So simple thing, we have got the relation. So the T square is directly proportional to R cube, Kepler's third law, right? So simply substitute the values now. So the TA by TB whole square is directly proportional to RA by RB whole cube. That's it. So now if we do the calculations here, so we have got TA. TA is the geostationary satellite, 24 hours is the time period, by TB whole square is equals to, directly proportional to, or else right you can equals to, right? Chalo. So here what is RA? RA is 6R, and what is RB? RB is 3R I can write, because this radius of the earth also you should consider. So 6R by 3R whole cube. Done. So 6R by 3R whole cube. So R gets cancelled here. So we can write, so this as 24 whole square by TB square is equals to, so this is 6 by 3 ones are 3 twos are, so 2 cube is 8, right? So I can write this as, so TB square is equals to, so 24 square, that means 24 into 24 by 8. So 8 ones are 8 threes are. So which comes out to be, sorry, calculation mistake, my bad. See here. So I can write, so 24 by TB. Yes or no? So the first one 24 hours, then by TB whole square is equals to, so this is what? So this is 8. So 2 cube is 8. 6R by 3R. So which is 2 we get. So 2 cube is 8. So then from here I need what is TB. Yes or no? So I need what is TB. So then I am writing, so 24 by TB. So send this to root 8, which is 2 root 2. So then I can write this as TB is equals to 24 by 2 root 2. So I can write it as 12 by 2 root 2. So which is 6 into 2 by root 2. So this 2 I can write it as root 2 into root 2. So 1 root 2 and 1 more root 2 gets cancelled, right? So which we left with 6 root 2. So option 3 is the correct answer, guys. Done, everyone? Clear with this question? Chalo, good. Now let's go for the next question. So the question number 10. So what's the question says here? The time period of a geostationary satellite is 24 hours. It is at a height 6 RE from the surface of the earth. See here. So the time period of another satellite whose height is 2.5 RE from surface will be same question. So there is satellite A, which is a geostationary satellite. 24 hours is the time period, and we have to find time period of the another satellite TB. Okay, and then so the radius of the first one is, the distance of the first one is 7 RE I am writing. Why? Because it is from the surface of the earth. So radius of the earth also you should write, right? And then what is RB? RB is 3.5 RE. 3.5 RE. So that's it. So we have got T square is directly proportional to R cube. So I can write TA by TB whole square is equals to RA by RB whole cube. RA by RB whole cube. So now from here I can write, so what is TA? Time period of the first satellite is 24 hours because it's a geostationary satellite. By TB we have to find whole square is equals to RA is 7 RE by RB, which is 3.5 RE. So again the same thing. So we have whole cube. So RE gets cancelled. 3.5 one time. So this is 2 times. So which we get it as, so 24 by TB, same previous one, right here. So which is equals to 8. So I get TB as the time period of the satellite B is 6.2 hours. That's it. 6 root 2 hours, not 6.2, 6 root 2 hours. Done? Clear? Got it, guys? Chalo. Good. Next. So let's go for the next one, that is the energy of the satellite. So if a satellite is revolving around any planet, so it will possess two kinds of energies. What are they? One is a potential energy because it is at some height, and then so the another is a kinetic energy. So the potential energy possessed by the satellite, which will be equals to minus Gmm by R. So let the satellite has some mass m. Okay, so then it is at a distance r from the planet center. Okay, so that minus Gm by R is a potential energy. And what kinetic energy it will possess? It is revolving around the planet with a orbital velocity of v0. So its kinetic energy will be half m v0 square, half m v0 square. So now the total energy possessed by the total energy will be equals to, so the summation of kinetic energy plus potential energy, right? So what's the potential energy? Minus Gmm by R plus, so what's the kinetic energy? Half m v0 square. So what is this v0? What is this v0? So it's with what velocity it is revolving? Orbital velocity, right? So let me do one thing, half into, so m into, so here the orbital velocity formula I am writing, so root over Gm by R whole square, root over, let's not write this step, so we'll simplify here and then we'll write the final thing here. So then R gets cancelled, so this becomes half Gmm by R, half m into Gm by R, right? So then I am substituting that here, so which we get it as, so half Gmm by R. So here if you observe, this is minus 1, this is plus 1 by 2. So the overall we get minus 1 by 2 Gmm by R. Yes or no? So minus Gm, this is minus 1, this is 1 by 2. So plus 1 by 2. So minus 1 plus 1 by 2 is minus 1 by 2, and this whole thing is same, Gmm by R. So this is the total energy which we write it as TE. So the TE is the total energy, guys. Understood? Clear? So just write it down. Chalo. So let's move further. So then we have got the next question. So what is that? A satellite of mass m is orbiting the Earth at a height h from the surface. So the total energy of the satellite in terms of G0, the value of acceleration due to gravity at the Earth's surface is. See here, first try to understand the given question. So this is the Earth. So from the surface of the Earth, a satellite which is of mass m, it is orbiting at a height h. So from the surface of the Earth, it is orbiting at a height h. This distance is h from the surface of the Earth. So now this whole distance will be small r. So what is this small r? Which is equals to radius of the Earth plus the height h. Done? Yes. Now, so what is the total energy? They are asking the total energy of the satellite. So what is the total energy formula we have got? So minus half Gmm by R. So minus Gmm by R. So but I need it in terms of G, small g and capital R. So in place of this Gm, so I am writing, so G0 R square by G0 R square m by, so the small r is nothing but, so the radius of the Earth plus height h. So check for this option. So minus 2 is not there in the numerator. So minus, so it should be minus first of all, minus mg0 r square by 2 into r plus h. So this is the correct answer. So the minus is also important. The total energy should be negative here. Done? Clear, guys? Chal. Sir, how you got this g naught into r square? So in place of this, see here, the small, I'll write here. So the small g is equals to gm by r square, right? Here they considered the small g as g naught. So that's why I'm taking g naught only. Okay. So then gm will be equals to g naught r square. So that's what I substituted here in place of gm. Done? Clear. Chalo. So let's take one more question. So try to solve this question on your own, guys. The additional kinetic energy to be provided to a satellite of mass m revolving around a planet of mass m. Okay. So satellite mass is small m and planet mass is capital M. So to transfer it from circular orbit of radius 1 to another radius r2, where r2 is greater than r1. See here. So first, this is a planet. So this planet has mass m. Okay. So now actually the satellite which is of mass m, it is revolving in a radius r1. So it is revolving in a radius r1 initially. Now it has to be moved to some other orbit where, so its radius should be 2r now. So 2r only, na? R2, not 2r, R2. So then what additional kinetic energy you should give? What additional kinetic energy you should give? So that's a question. So try that. See, the addition, first what is the total initial energy and what is the total final energy? So you can just simply write that. Kinetic energy always supplies energy to the satellite, guys. So here, initially, what is the total energy of the satellite? What is the total energy of the satellite? Tell me. So initially, we have got half g, the mass of the planet is m and satellite is of mass small m. And the radius is RA. And what is the final when it is shifted to the radius R2? So its total energy will be minus half into GMM by RB. Its mass will not change. The mass of the satellite will not change. The mass of the planet will not change. So they both will be same. So now what is the additional kinetic energy? So which is equals to additional KE is simply TEF minus TEI. That's it. So the final total energy minus initial total energy. So if you subtract, we get minus of 1 by 2 GMM by RB minus of minus. This will become plus half GMM by RA. That's it. So if you take half GMM out, so that we get 1 by RA minus 1 by RB. That's it. So this is the final one. So half GMM 1 by RA. RA means R1 here, then R2. So yes or no? So RA means R1 and R2. I can write R1 minus R2. So in terms of 1 and 2 you write. So 1 by R1 minus 1 by R2. So better write this way. So here also. This is R2, this is R1. Done. So this is 1 by R1. So this term is minus 1 by R2. So option 4 is the correct one, guys. Done. Clear? Chal. Next. So now, what is the relation between kinetic energy, potential energy and total energy of the satellite? Simply remember this one. So we have got, the potential, let's write all the formulas at one place first. So we have got the potential energy is minus GMM by R. Yes. And then, so the kinetic energy, actually it is half m v naught square. So from here, half m into v, in place of v naught, we are writing the orbital speed. So which is root over gm by r whole square. It becomes half gmm, yes or no, by r. And then the total energy, which will be minus of half gmm by r. So this is what we got. Yes. Now if you observe, I can write like, so the total energy, understand this statement properly. So the total energy is this is a total energy and this is a potential energy, right? So the total energy is potential energy by 2. The total energy is potential energy by 2. So which is equals to negative of the kinetic energy. Just try to understand this statement. So if you observe, the total energy and the kinetic energy, they both magnitudes are same. 1 by 2 gmm by r, 1 by 2 gmm by r. So but they are differed in sign. So that's why the total energy is equals to negative of the kinetic energy. And so if you observe here, in place of total potential energy, which is equals to minus gmm by r. So I'll write here. See. So here, let me do one thing. So 1 by 2 I am writing aside into, so minus gmm by r. From this total energy formula, I am just rearranging. Half into minus gmm by r. So half into what is this minus gmm by r, which is nothing but the potential energy. That means the total energy is half of the potential energy and the total energy is a negative of the kinetic energy. That's what I wrote. So the relation between these three is, so the total energy is equals to half of the potential energy and which is equals to negative of the kinetic energy. Done? Clear this part, guys? Everyone? Yes, very good. Remember this relation. Again, you will get this in electrostatics. Okay, the same relation but in terms of electrostatical energy. So now what is the binding energy? So the binding energy is nothing but it's the negative of the total energy, guys. So you can simply remember, so it's a negative of the total energy. What is the total energy we have got? So minus gmm by 2r, right? So the binding energy is equals to negative of total energy. So which is minus of, what is total energy? Minus 1 by 2 gmm by r, right? So minus of minus plus, it will be gmm by 2r is the binding energy Be. Simply remember the formulas. Done? Chal. So for a satellite moving in an orbit around the earth, so the ratio of kinetic energy to the potential energy. So the ratio of kinetic energy to the potential energy. So what will be the ratio? The ratio of kinetic energy to the potential energy. If you want, you can write the formulas. So the kinetic energy is equals to half m v naught square. So what is this v naught? Half m. V naught is root over gm by r whole square. So square root gets cancelled. Half gmm by r. So this is the kinetic energy. And then, so the potential energy we already know, minus gmm by r, right? So then they are asking, so the kinetic energy ratio to the potential energy ratio Ke by U. What is Ke? Half gmm by r by, what is potential energy? Minus gmm by r. So I can write, so gmm cancel, r gets cancelled, right? So which we left with 1 by 2 minus 1, which is nothing but minus 1 by 2. You can just simply take the magnitude so that it will be 1 by 2. So the ratio is going to be, so 1 by 2. Clear? Done? Yes. So then next, the next question, question number 14. So the satellite of mass m is orbiting around the earth in a circular orbit with velocity v. So what will be its total energy? So what will be its total energy? So I know the relation, the total energy is equals to, so negative of the kinetic energy r, so the potential energy by 2. So it is orbiting with a velocity v. It is orbiting with a velocity v. So I can write the total energy is equals to, simply I am going to take this relation, minus kinetic energy. So minus of, so it's moving with v velocity. So its kinetic energy will be half mv square. So the total energy should be minus half mv square. So the total energy is negative of the kinetic energy, which is minus half mv square. Done? Clear, guys? Chalo. So there are two satellites of Earth, S1 and S2 are moving in the same orbit. Fine. So the mass of S1 is 4 times the mass of S2. So then which of the following statement is true? So the potential energies of Earth and satellites in the two cases are equal. The potential energy, it will depend on the mass of the satellite. Yes or no? See here. So the potential energy is it depends on the satellite mass. See here. So it depends on the satellite mass. So that's why. So the potential energy cannot be same because their masses are different. So this option is wrong. So then S1 and S2 moving with the same speed. So the orbital velocity, which is equals to root over gm by r. So orbital velocity is independent of the satellite mass, right? So that's why. So though their satellite mass are different, so their orbital speed should be same. So second is the correct. So the kinetic energy also depends on the mass of the satellite. So it cannot be equal. Time period 4 times. Time period also will be equal if the statement is there. So time period also will be equal because the time period is 2 pi into root over r cube by gm, right? So the time period is independent of mass of the satellite, guys. Okay, so if the time period is equal statement is there, you can choose that also. But here they said it is 4 times that of the S2, so which is not possible. Done. Understood this part? Chalo. So that's it from my end for today's session. So in the next session, we'll come up with a new topic. So till then, keep studying. All the very best. Bye guys.